Good afternoon and welcome to this week's episode of the CERIAS Security Seminar live from Purdue University. I have dropped in the notes that if you have not, I wanted to notify you that the registration is indeed now open for the 24th annual CERIAS Symposium at Purdue. The address www.cerias.purdue.edu/symposium or visit our website. But today, it is my distinct honor to be able to introduce our guest. So I have been at CERIAS for about 17 years. I'll be coming up on my 17th anniversary. So I guess one of the nice things is that when you've been around this long and great faculty continue to do great research, that they get invited back, that this is actually the second opportunity that our speaker today has been able to speak in the CERIAS seminar. So again, it is my distinct honor to introduce Dr. Albert Cheng. Professor Cheng is a Fulbright specialist and both a full professor in computer science and a full professor in computer engineering at the University of Houston. Albert, great to have you back on campus, unfortunately virtually this time, but great to have you nonetheless.
Thank you very much, Joel, for the outstanding introduction. Yeah. So yeah, and I also confirm that you can record my talk. So please do so. Yeah. All right. So welcome. So in this talk, short talk, 15 minutes, I'm going to tell you a little bit about using regularity-based virtualization and also functional reactive programming to make real-time systems, cyber-physical systems, embedded systems more robust. First of all, I'd like to congratulate Purdue's CERIAS for the 25th anniversary of its founding, and I'm proud to be part of CERIAS history. As Joanne mentioned, I gave a talk, that was 16 years ago on March 28, 2007. And I gave a talk on verification of real-time systems and intrusion detection. And my host at that time was, very friendly, David Yao. So again, congratulations to 25th anniversary of CERIAS founding. All right, I also like to thank you, my own research group here, who has done all, excellent job in basically getting the results and some of which are presented here. So my current research group here, PhD student, undergrad, and scholar, visiting scholar. So you can see pictures, recent picture, it's a group meeting that's virtual. And then before the pandemic, we have larger in-person meeting, parties, and also visit to interesting site like the Arecibo Observatory in Puerto Rico, after RTSS 2012. And RTSS Real-Time System Symposium, it's our flagship conference, in real-time system. As Joanne mentioned, I'm a Fulbright specialist. And my term, runs until the end of 2024. And a recent assignment was to Panama. And here's a letter from President Trump at that time, Panama Canal. And the goal was to help the universities there to enhance the research capabilities and also improve their graduate and undergraduate research programs. So I also travel a lot, like in these two slides, you can see University of Washington, Rome, Oxford, giving talks on different subject topics, to Caltech, TU, Technical University of Vienna, at CPS Week, and also UC Berkeley on the lower right. So it's always great to really interchange ideas with all of you. And I'm very happy to be here second time at Purdue and exchanging ideas and hopefully engage you in research in embedded systems, real-time systems, and cyber physical systems. All right, So the focus here, maybe it's different from what you usually see. And basically, we're looking at real-time embedded system that are controlling safety critical processes that have timing constraints, not real-time constraint. So not only you have to be logically correct, but also timing correct. So you have to meet the timing constraint. So for example, an airbag system in your car, there's a collision, and then the airbag has to deploy within 15 milliseconds or less, right? So it's not good enough for the airbag to deploy, to inflate, but if it's late, let's say 2 seconds later, it's not useful, although the airbag inflates, right? But it's not doing it within 15 milliseconds. So timing performance is critical to the correctness of the system, right? Not to mention, we can encounter intruders attack, right? That can compromise the security and safety of the system. So today we're going to focus on monitoring and control systems in a modern real-time system. So you have a decision system, a control system that is based on computer hardware and software. And you have a target system that is under control. It could be chemical, fluid, electrical, mechanical, and thermal. And then in between the signal processing, right, you have the energy conversion that shows you basically parameters, real-time parameters from the target system. And based on this, you're supposed to, the decision system is going to actuate, right, again, energy conversion, power modulation, that will send signals and then maybe open a valve, maybe cause the chemical in the airbag to explode so that the airbag inflates, within 50 milliseconds. Depending on the system that is, under control, it will basically be affected. And the goal is to ensure safety and progress of the target system. And individual system like this could be networked to other embedded system, forming a more complex real-time system, could be a cyber physical system. And of course, the user interface is very important. But today we're going to focus on the part D. So basically the control system that is making the decision to make sure that the target system operates safely and reliably, always on time. So a little bit about real-time systems theory, especially for those of you who are not familiar with this. So this is obviously a real-time system, it's the Mars rover. And one of the problems that has been publicized in one of the missions is the problem with the priority inheritance protocol. So basically the system kept shutting down, right? And the higher priority task does not get to execute, right? So a scientific experiment could not be done. And new version of the software has to be uploaded to the system after several days of exploration and finding out the bug. So our goal is to make systems like this more robust, okay, more robust, more reliable, right? So we can defend against programmer errors as well as unwanted intrusion by basically actors who are determined to do harm to the system. So a little bit about the theory is necessary, right, to understand further the seminar. As you know, the more components you have in a system, the more difficult it is to build and to maintain. And we want to build a system that is robust and secure. So we have to build a system that does not fail, quickly. If there is basically a fault in the system, it could be because of a programming error or because of an intrusion. So we want to make a system as robust as possible. So in a way, if you think from the security point of view, is to reduce the attack surface, that the intruders can get in. All right, so in real-time systems, we talk about preemptive scheduling and also non-preemptive scheduling. So preemptive scheduling may not be suitable all the time because we have to ensure critical section for certain portions of the code. And however, it has overheads because you have to do context switches. However, the schedulability is increased if you have preemptive scheduling versus non-preemptive. So there are issues that you'll see there's trade-off in the design and implementation. So as I said, with preemptive scheduling, you have more likely to find feasible schedule meeting all the deadlines. But with non-preemptive, it's easier and it prevents the priority inversion problem that has occurred in the Mars rover, one of the mission of the Mars rover, and obviously less complex. But with non-preemptive, you're going to get fewer feasible schedules. So another way to simplify this, as you'll see later, right, to ensure we have fewer errors, fewer synchronization problem, is through the use of functional programming. Or you can also restrict the periods, the sampling rate of the task to be harmonic. I'm not going to details of this, otherwise I cannot go to the main point. So I will flash through these slides, and then if you have questions, you can ask me at the end of the lecture. So this is showing harmonic task sets. So meaning the periods are multiples of each other, right? And this is believe me, it's a good schedule meeting the deadlines of this periodic tasks. So another example with more tasks, so 7 tasks, again, harmonic periods. And again, this is a good schedule, meeting all the deadlines. Now, let me define what is a real-time or embedded system. So an embedded system, it's a computer system that is designed to do something specific, to control functions within a larger system. That's why it's called embedded, right? So the computer hardware and software is embedded into something more complex, something larger, like a late model sports car. And constraint, you're not just talking about timing constraint, like deadlines, but also there's a memory size constraint, there's power, right? Imagine this is a portable device with an embedded computer, right? You need to do various monitoring operation. So there's power constraint, right? So you cannot run it, at the highest voltage or frequency, because then you need to recharge your device very soon. Obviously, there's also size constraint. So you cannot fit in an entire data center with all the servers in a small system like this, or like in a satellite, right? Or in a portable device. So embedded system is, in short, a computer that's embedded into something more complex. And the main function is not just computation. Like in a car, is to move you from point A to point B safely. Now, you probably have heard about other terms such as cyber physical systems. So it's a fusion of computation, communication, and physical elements. And then later we'll talk more about the functional reactive systems, which are basically real-time systems that uses functional programs as the code, the core part, right, of the monitoring and control mechanism. And I already mentioned the complexity, right? So not only you need to meet logical correctness constraint, but also timing constraint, right? You have to execute the task, finish the task or the thread within the specified deadline every time. And the timing constraint obviously varies from one application to another, right? So if you're talking about a car, you're talking about millisecond performance. If you are talking about a nuclear physics experiment at a linear accelerator or at the CERN in Europe, you are talking about below nanosecond performance. So complexity is a major issue. Today, we're going to focus on robustness and reliability, right? How to make the system more robust, against errors that are, could be programmers induced, or it could be something outside the system that would require us to design the system in a fault-tolerant way. Security and privacy, I don't need to say much. The whole center here is devoted to this area, and it should be a first-class design issue. It should not be an afterthought, right? Because any weak point in the system, small devices could be the most vulnerable, right? In an Internet of Things or cyber physical system. So functional reactive system is systems that react, to the environment being monitored and controlled. And later on, we'll show how functional programs help with making the system more robust. And I'm going to show you several examples, like of reactive systems, light switch, and thermostat, climate control systems. So these are soft, real-time reactive systems. And if you have a pacemaker or a anti-lock brakes mechanism, that would be a reactive hard real-time system. So CPS, or cyber physical system, it's the fusion of computation, physical devices, and also communication. So we can see state-of-the-art CPS involving maybe robotic surgery. And here is transport vehicles from the military. So the current set of tools are not able to really handle the complexity at this point. So more research are ongoing. And our job is to make the controllers more robust. As I allocate, we'll be using virtualization and also FRP, functional reactive programming. So another area where you encounter this, so I mentioned automotive and medical, you'll see the grid, the energy grid, it's a CPS. So this is conventional system, right? So the generation of the electricity to transmission, distribution, and usage. So enter a smart system. You talk about smart meters. You talk about using very accurate weather prediction so that we can use green energy as much as possible, as opposed to coal and basically more polluting energy sources. Again, intrusion detection is it should not be an afterthought. So there's always some bad actors who want to maybe do harm to the system. And also in my research is to allocate using formal methods to ensure the system is really safe. So here's a picture diagram showing a smart system, for the energy production to consumption, a CPS for the grid. And the goal is to use green energy as much as possible. We want to avoid blackout or problem, let's say, with a freeze like years or a couple of years ago in Texas. So, the freeze caused basically the electric supplier not being able to supply electricity to all the homes. But of course, there are some other issues involved in that one. But many years back in California, it's the same issue. So it's, because of the sudden demand in electricity usage, it's basically many homes, had rolling blackout, same thing for industry. And we like to avoid that with smart meters, with machine learning, with accurate weather prediction, and looking at the history of basically past usage and real-time usage of residential and commercial customers. Another application, right, a domain, it's air travel. Can we build systems that are so robust and secure that it can actually override human errors or rogue actors in this system? So can we build systems that automatically avoid collision, whether the airplane is on the ground or above ground in the air? And I think lately there were several incidents where there were near misses, airplanes very close in colliding with each other on the ground, at the airport. So how do you prevent that automatically? It's the goal of building CPS, robust CPS for air transportation. So in this, an envelope is allocated, and to ensure that basically, airplanes are safe from each other, from colliding with each other, and also to override human errors or maybe even rogue pilots on suicidal mission, right? But right now we are far from doing that because it's the other way. So the machine may make errors that cause airplanes to crash, like the Boeing 737 MAX accidents, at least 2 of them. So we're still, at the infancy of the research, and how to build robust system is more important than ever before, because with so many complex systems, both hardware as well as software, which you cannot so easily visualize. Okay. So a high-level diagram showing the envelope around each airplane, making sure that they do not come into contact with others. So the goal here, is to develop tools, and platforms to make basically CPS more robust and more reliable. And again, verification tools are allocated. So another example here, before I go into the key points, it's the SATS. It's a protocol to land small aircraft without the instructions from air traffic controllers. And this could save a lot of money. So many years ago, there were a budget cut, and they were talking about, government was talking about cutting the number of traffic controllers in smaller airports. And a protocol like this, would be very useful. And we have actually analyzed such a protocol from developed by NASA using real-time logic, which is a logic that allows you to reason about real-time events. So it's an enhancement of first-order logic. All right, so now we are on to element number 1, that to build a robust real-time system. And that is using virtualization, and in particular, regularity-based virtualization. As you know, virtualization is increasingly used not just in conventional system, but also in embedded system, right? And this is to enhance the safety, robustness, and security. So the virtual resource that is allocated to an application is guaranteed to meet the timing constraint of that application, if it's an embedded application, and also isolate itself from others, for robustness and security purposes. So what virtualization does is to divide the hardware resources, such as cores and processors, into temporal partition and allocate as virtual machine or resources, right? So several virtual resources on the same physical core can be allocated to different applications. There are 2 problems here. So one is virtualization underutilizes the hardware resources in order to provide the real-time guarantees. Second, the periodic partitions that were, pretty much the norm in real-time virtualization fail to effectively bound the difference between the ideal and the actual resource allocation. So ideally, I like to have maybe every interval of time, periodic interval of time, I have this much physical CPU allocated to a set of tasks. But in reality, this fluctuates a lot, and it may deviate too much from the ideal. So these are two problems that make virtualization not so appropriate, especially for embedded and real-time system. So the solution is to employ the regularity-based resource partitioning model, which we have worked on a lot and also enhanced, and it's we have shown it to be theoretically superior to other models in existence. So it uses the concept of regularity, and I'm going to explain shortly what that is. And it provides a near ideal supply to all the virtual machines. So the actual resource allocation is very close to the ideal. And that is important because if you are guaranteed a share of the CPU, then that guarantee should be happening all the time, not just once in a while. At the same time, with RRP, we achieve the highest utilization. And this is by not just 1 or 2%, but this is by 30% or more versus the other models that are available. So let's take a look. This is a high-level diagram showing a physical resource is partitioned into multiple physical resources, okay, or virtual machines. And then each virtual resource is assigned to execute a different task, right, in different applications. So basically, you have a hierarchical real-time scheduling system. Real-time systems are not static. They are continuing evolving, right? So continuously evolving. So they are called CERTS, right? Continuously evolving real-time system. And if I'm running the CERTS on non-virtualized platforms, so basically I have to certify and verify each pair of CERT and each hardware. But if I'm doing it with virtual machines, then I only need to verify one pair of CERT and EM hypervisor. So this is more efficient than non-virtualized system. And in fact, we have implemented RRP on Zen, which is an open source, very popular virtualization platform, and also on Extractum. It's a bare metal embedded hypervisor. So more about this shortly. So a little bit on the research here. So too much to really squeeze into a 50 minutes talk. So basically, 10 years ago, more than 10 years ago, in 2011, so we extended the existing work at that time on RRP from a single resource to a uniform multi-resource platform. And this is necessary so that it's applicable to multi-core computing platforms that are prevalent today. We also increased the utilization, making it attractive, right? But before that, basically you reach 50% of the utilization of the hardware resources, and you cannot go further and still being able to guarantee the real-time performance constraints. And then in 2016, we achieved maximal transparency for task scheduling in the sense that the resource scheduler, right, basically does not need to know much about the task level parameters. So making it possible to run legacy system, real-time system on virtualized system without any modification. So that really simplified resource allocation and makes programmers, happy with this new enhancement. And then in 2017, we provided basically advanced approximation techniques that allows RRP and its partition scheduler to outperform any existing global scheduling algorithms available. Right? So these are great advances that makes virtualization attractive and in real-time system and making them more robust. So let's look at the first paper, the 2016 paper, that's on temporary resource partitions. And basically, we are dealing with weights. So more weights means more compute power for a specific task group. And the goal is we want to make sure that we have fairness, performance, and real-time determinism. So there are two issues. So one, we can make the resource partitioning simple, or we can make the task scheduling simple. There's a trade-off here, right? End users obviously don't like changes, right? So you don't want to ask the programmer to change the software. It's already hard to develop and debug and validate. So we want to keep the simplicity on the task scheduling intact. Instead, we work on the resource partitioning level. So this is a graph showing time and the supply. And the ideal line, the blue line, shows the availability of the hardware resources. And we do not want basically the real supply at runtime to deviate too much from the ideal line. But with existing technique, the periodic resource model, it may deviate much more. So with RRP and our enhancement, this is very close to the ideal line, so that the red line doesn't go too far off. So we define that a resource partition is transparent for a scheduling policy and a task model if we can directly use the corresponding dedicated resource scheduling algorithms to solve its scheduling problem. So no modification. And that's the objective in this paper, and using the idea of coarse-grained scheduling as a bridge. Right? So we basically make a virtualized system using RRP and our enhancement, and to make scheduling, and I'm not going into details here because of the time. So we want to make the scheduling as easy as if you are scheduling the application task on a dedicated machine and not on a virtualized platform. So that's enabled by the result in this paper, right? So making this equivalency. That's one step. The other one is to make utilization as high as possible. Recall that one of the two problems is that it's hard to use a virtualized system and still maintain a high utilization. Basically, you are capped off at about 50%. So imagine you buy a 3 gigahertz computer, you basically end up with a 1.5 gigahertz computer. So that would not be nice, to do if you use virtualization and you basically cut your compute power in half. That would not be a good sale for using virtualization. So we were able to increase the utilization again, using in this model. And the way is we start with the transparent task scheduling technique in the 2016 paper, and then in the 2017 paper, we basically enhanced the algorithm from 2012, RTSS 2012, to make it into something called MUZ, or multiple Z approximation sequences. Okay, it was published in ACM Transactions on Embedded Computing System, 2017. And the idea is to assign regular partitions to resource units and then schedule them on each resource unit. And the results of a single resource scheduling are critical for a partition scheduling, as we have found out. So we have this EABS, for extended approximation boundary sequence. So this is needed to ensure that we have a supply, a real resource supply that is very close to the ideal supply. So approximations are used, right? So the ideal line, and we want to keep the red as close as possible. And we have this EABS working together, and on single resource as well as multiple resources, right? So these are showing different sequences. Again, I'm not going into the details of the math here, but the goal is to show that there are different approximation overhead depending on the approximation sequences. And we choose the one that is most appropriate for the weight, for the resource supply that is desired, that is required by the application. And working with this, we find out that you can see the red line. That's our newest algorithm. Basically outperforms the other existing algorithm. Like the green is the global scheduling algorithm. Okay. And looking, the horizontal is the weight, and the vertical axis is the schedulability. And you can see that we can push toward 93% or more. Okay, so very exciting result. Compared with the green, you can see more like 80%, 79%. So a 20+ increase in the percent increase in the utilization of the hardware resources. All right, so not happy with just increasing the utilization and making task scheduling transparent, right? We also incorporated fault tolerance into this model. So starting with 2017 and also 2018. So the goal is that if there are faults occurring because of, let's say there are transient faults, due to stress on the semiconductor, or it could be fault induced by an attacker that attempt to change the timing performance, like delaying completion, could be a fault. So we want to make it basically more reliable by using checkpointing and then re-execution of the part of the code that experienced the fault. Okay. So again, I'm not going into the details here, but using checkpointing as well as varying the interval between checkpoints if there are no faults, and that way to reduce the overhead needed to incorporate this fault tolerance mechanism. All right, so not only we have developed the theory which have predicted high utilization, transparency, and also adherence to the ideal supply, right, with the real resource supply. So we finally implemented after several years and several staff members working on this, mostly PhD students. So we implemented RRP and enhancement on SEN, and this was reported in ACM LCTES. And the artifact is available. You can download and try it out. And also on Extractum, and this was reported in IEEE Transactions on Computers. And then the fault tolerance mechanism was reported at RTSS and RTAS. And the research continues. So we want to build actual system that are fault tolerant on actual hardware, that are robust and very safe against intrusions that can affect the timing performance as well as the logical performance. The second part of the talk is how to use functional programming and what it means for building robust systems. So functional programming is it's something that is like programming with mathematical functions. And the functions either evaluates completely or not at all, right? So it's all or nothing proposition. Examples, from Haskell, Atom, Erlang, STRL, and F# by Microsoft. So because these are math function or something close to that, we can compose them more easily. We can verify them more easily. And you'll see shortly that we don't need synchronization primitives like wait and signal. And we can avoid priority inversion altogether. So in the next few slides, this is in Haskell, and it's a simulation of the anti-lock break mechanism. Again, I don't have time to actually go into here, but you can certainly review my video later on, and you can see that this simulates a four-wheeled vehicle, and they're basically the wheel spinning, and the goal is to brake and stop the vehicle. Right. So we start out with the wheel spinning at different speeds, and we want to ensure that we go to the same speed because some of the wheel may be locked, is skidding on the surface, and the goal is to reach to make sure that all the wheels spin at the same speed. And of course, if you need to brake the car, you need to make sure that all the wheels spin at zero, right? The speed would go to zero. So FRP is similar to like data flow programming, but there are, there's some differences as well. And it's basically a programming paradigm where programs are inherently stateful and can automatically react to changes. And FRP allows intuitive specification and formal verification more easy compared to procedural languages. So, so FRP is similar to data flow, but it supports higher order functions. So it's a type-safe language. It can model discrete and continuous aspects of events, and it's a transactional model, right? Similar to database transactions, and synchronization primitives are not required. So it's ideal for parallel execution. Weakness, okay, this is still new, in the sense that it has not been used in the mainstream for controlling real-time system. But the strength is, as I mentioned, it's very easy to compose. It doesn't require synchronization primitives. But one problem is that the model requires you to execute a function entirely or not. So if during the execution of a function it's interrupted, then you have to resume from the very beginning. So let's take a quick look. So, to preserve in conventional system, we need to have mutual exclusion, right? To access shared resources. And mutual exclusion can incur delays like this. The private here is using the table, there's only one, and the general much higher priority task may have to wait, until the private finishes, using the table. So let's look at an example, right? Instead of going to the definition, let's look at a simple example. This is a car controller. So C is the worst case execution time, T is the period, and D is the deadline. And these are the parameters, right? And we want to try any method to schedule the tasks. So easy way is it's a cyclic executive. It's basically a table, but it's not very flexible. So you basically split the unit processor system between the tasks like speed measurement, ABS, and checking the field and repeat. And you may use different concurrency mechanism to ensure there's no priority inversion. Now enter FRP or priority version of this. Right. So here is a copy and restore operation. So let's look at this example. So if a lower priority task is aborted, terminated by a higher priority task, the lower priority task has to start as a new one. So it's not a preemptive scheduling. So you can see tau 2 here is the up arrow means the task arrives at that time. So tau 1 has higher priority, it arrives at 3. It kills task 2. And you can see task 2 with the execution time 4. So WCET is the worst case execution time. It has to restart from the beginning. So you waste the execution time, the 3 units at the beginning. This is not the case in conventional system. Okay, so analysis tool needs to be developed for FRP, even though it's a great programming paradigm and it can reduce errors in programming and also makes it easy to verify. It's more robust, but you incur this wasted execution time cost. So we need to develop tools to analyze this and also mitigate this. Okay. So again, these are the benefits I mentioned. So very limited work on schedulability and analysis. So that's why we came in. And we focus initially on exact analysis. Right? So basically, we look at the time that is lost, and that could be interference and also abort. Interference means interference by higher priority task. So if you are the highest priority task, then your response time is simply your worst case execution time. But if you are the lower priority task, then you need to add the interference and the abort cost. Again, I have to go through this quickly, right? Because 15 minutes is up very soon. But I think you get the idea. So you have this sum of the ceiling of this expression in order to obtain the response time, right, in the worst case. And that this is the maximum abort cost. And finally, we can arrive at a precise number. Say more efficient analysis would be an approximation of this, and we have done that also. Right? And I'll show you, this is about the ABS. So again, the same example. This were my 2 undergrad students who did research with me, and very proud of them. So this is an example with rate monotonic scheduling. And this is just conventional, not FRP. So you can see C, the response time is 3, its original execution time. You can see here, 3, plus the time needed for A and B, because A and B are higher priority, so they have to be executed first. And the response time is 6, right? So your own execution time plus the execution time for A and B, right? Higher priority. But with FRP or PFRP, you have the abort cost. So the red area indicate the wasted execution time. So now the response time of C is no longer just A and B, but also the wasted time, because C was basically interrupted by B and A. Right? But still at 14, it meets the deadline. So we need to develop the analysis tool for this in order to make FRP works for real-time system, to make them more robust. So I'm going to flash through this quickly. And the goal, of course, is to stop the car, real system, real impact. And finally, avoid hitting an obstacle like a deer, right? So who is going to be very happy, right, that this works as specified. So this is a high-level code of an exact analysis. We have several approximation algorithms that will return the result more quickly. Not only we are analyzing the CPU time, but also the memory. And we started out by looking at the scratch pad, which is a simple cache. Analyzing the entire system with different levels of cache is in the works, so that we can make FRP ready for prime time in real-time system. So again, I'm not going to show you the details here, but basically this several slides deal with the scratch pad, right? So eventually, we also want to analyze the cache. And our results are very close to the predicted. So the estimated time is very close to the simulated execution time, except one of these in this benchmark study. All right. And finally, let me conclude the talk by saying that with virtualization, especially with our model, RRP, and also with FRP, we can enhance the robustness and safety and performance of a physical system, right? Like a real-time system or cyber physical system. And virtualization is a great to isolate the intended application from other applications. FRP is great as a not just as a programming language, but also as a specification language, and it allows formal verification more easy. And the research impact is obviously to facilitate the design and the update, because these systems are continuously evolving, and we want to make sure that they meet the timing constraint and logical correctness constraint, in addition to be reliable, robust, and also reduce the attack surface by intruders. So thank you very much for your attention. A little bit of advertising. So if you are curious to find out more, you can read my textbook. Check out the earlier workshop that started all this research in San Antonio, in Vienna, in Seoul, South Korea, and also at ASPROS in Providence. And finally, last December in Houston. This is a picture of NASA on the right with Edward Lee from Berkeley, and with my student Jennifer G. Wu Lee at RTSS, back to in-person hybrid, last year. So thank you very much, and the rest are just the references, right? So let me just show them. And Joanne is waiting. Then there are many references, and I think there are 11 or 12 pages, right? All right, and let me go back to the thank you slides. And thank you very much. It's a pleasure to be here, and I hope to see you in person in the future.
Wonderful. Albert, thank you so much for the great presentation. Those in attendance, if you have any questions, please drop them in the Q&A box. We are over the 5:20, but as normal, we usually stick around till 5:30 if there are questions. So Albert, I'm going to get my calendar out here and put an X on 16 years from today so that you can keep your cadence going. So 16 years from now, we'll have you present again, all right?
Definitely. It has to be in person.
No, let's try to make it sooner than that.
Yeah. So I don't want you to retire or me retiring.
Well, it looks like we don't have any questions, so we pretty much finish on time. Albert, again, great to see you, my friend. Thank you very much for participating. Students, we will be back here, or all attendees, we will be back here next week. Do note that during Purdue's spring break, student spring break, we won't have a seminar that week, but we will pick up after that. We'll continue through the semester. We'll take the break during the summer and then start again in the fall. So several more through March, April, and into early May this semester. And then one more time is that hope many of you, both on campus as well as off, will have the opportunity to attend the 24th annual CERIAS Cybersecurity Symposium at Purdue. And the registration can be found along with the full agenda for the event at our website. So with that, we'll call it a day. Thank you very much. We'll see you all next week.
Yeah. Thank you, Joy. Thank you, and have a great spring break.